Welcome back, everybody. Let's continue with a question on Zoom. So the question is about what happens. So I showed you the whole thing with the binary search and that it's sorted data, and then you can use binary search in order to find anything in logarithmic time. Now, what happens if the table is not sorted? Well, the idea is that in any case, we build an index, right? And the index you can build whether or not the table is sorted is irrelevant, because what you do when you build the index is that you go row by row through the data and add every record to the index. In fact, when you are building the index, you are in fact sorting the data, but you are sorting the data, putting it in a structure that facilitates the binary search. So what I showed you at the beginning last week about the sorted data in the binary search was an introduction to what happens, imagining that it's a human that actually does that. So if it's a human who looks at the sorted table, then they use binary search to find the value in logarithmic time. The way a computer does a binary search is like this. This is in fact a structure that facilitates a binary search. And if you look at it, this is in fact sorted. And the way I see that it's sorted is that technically you can traverse the data like this and output in linear time, so very quickly, everything in a sorted order, very efficiently. But you see that this in fact is a binary search. When you traverse and look left and right, you are in fact doing a binary search. So again, what I showed you with the sorted table was only an introduction, a quick intro to indices, but in fact, we are really building it in this way, right? Does it answer your question? Sign of life, maybe? I'm assuming I answered the question. All right. What I wanted to say also, or let me ask you, what do you think is the complexity of building that? For anybody who knows complexity, I know that most of you didn't study complexity theory, but in terms of n, 1, log n, and so on, what is the complexity? Yes? O of n, that would be nice, right? So the hash table you can build in O of n. So for building the hash table, yes, because every time the hash function is O of 1. But the tree, sadly, we cannot do it in O of n. It's slightly less than that. Does anybody know that? How much it is? Yes? N log n, exactly, you got it right. This is n log n. And the reason is that you traverse the table, so you get the n for traversing the table. But every time, in order to insert into the tree, you need log n. So this is why you have n log n. So it's not exactly linear, it's a bit less than linear, but it is n log n. And in fact, you might know that the best sorting algorithms are also in n log n, right? So you know, have you heard of bubble sort? Yes, so bubble sort is very inefficient, right? There are better algorithms that do it in n log n. In fact, there was a very funny video, I think it was it in 2008 or 2012, during the presidential campaign, Barack Obama was invited to some summit with technical people, and you can find it on YouTube if you search. And so they were having a discussion, and then there was one of the leads, I don't know if it was the CEO of Google or something like that, but basically asked Barack Obama, like, what is a good sorting algorithm? And then they kind of were about to just withdraw the question, like, no, I'm joking, you don't need to answer. And then Barack Obama was like, no, let me answer. You should not be using bubble sort. And that was like big applause in the entire room. So yeah, basically the best sorting algorithms give you that in n log n. All right? And it's not a coincidence, because when you build a structure like that, you are in fact sorting the data. So this is actually one of the fancy ways of sorting data. Okay, so next time you have a card game that you need to sort, you can try to see if you build a tree like that and get the card game sorted in n log n. Yes, go ahead. Oh, so the smaller and the greater is by definition of the table. So this is a constraint that you have on the table. Now, what you put in the nodes for the comparison is kind of depending how you build it. This basically happens on the fly as you build the table. But I will have an animation for you that will show that to you. Any other questions? Yeah. All right, let me continue. So now these were binary trees so far, which is kind of the start of B+ trees, right? But a B+ tree is slightly more complex than that. In fact, in that case, I only have 2 children. So 2 children is fine. That's kind of a binary search. The problem is that the index in the end is going to be stored where? On the disk, on the hard drive in general. Sometimes you can fit it in memory, but very often it's going to be on the hard drive. Now, you're obviously not going to access everything on the hard drive. You're only going to access the parts that you actually need to read. So basically, if you imagine that you're looking up not like this, you go like that, and that's the only thing you're going to read from the hard drive, right? Now, you might know that when you read from a hard drive, you never read just a few bits. That never happens. Whenever you read data from a hard drive on your laptop, you always read something like 4,000 bytes at the same time. 4,000, it's a block of 4 kilobytes. The reason is that if your laptop was trying to read the disk byte by byte, like give me that byte and give me that byte and give me that byte, the head of the hard drive would go crazy because it would just jump from place to place giving the bytes. That's highly inefficient. So in order to prevent that, what you do is that you always ask for 4,000 bytes at the same time. And then you get the whole 4,000 bytes. So we like to read things that are kind of located together. Now, if we use the binary tree like that, these nodes here are not. What kind of size it has? Just a few bytes, right? Imagine even if it's UTF-8 or something, that's like 3 bytes in there. Maybe there's additional bytes for the record and so on. But you see that it would be extremely inefficient because just to read these few bytes, we would request 4,000 bytes from the disk, right? So we are underusing the possibilities of the disk. So in order to optimize and make the whole thing more efficient, we are going to allow for more children, not just 2, but more. Like in that case, it's 3 children, right? And you see that what happens when I do that is that my nodes are a bit bigger. And ideally, I'm going to add as many children as I can in such a way that then the size of the node would be just about 1 block of the disk, 4,000. An immediate consequence is that it reduces the depth of the tree. Because if I have more children, I'm going to squeeze the tree into less levels, right? Who sees that? Okay. This is the reason, right? And the reason is, again, we want to have these larger nodes because we like to read in block from disk, and so we can squeeze more into a single read from the disk. All right. So the idea is that instead of just binary, it's going to have more children. And so in a B+ tree, there are a few constraints. For example, in a B+ tree, we strictly require balance in the sense that we want all the leaves at the same depth. Here, all the leaves are at depth 2, right? 2 levels below the roots. We do not allow a leaf to be at another depth. Like you cannot have some leaf 3 levels below and some other leaf 4 levels below. That's not allowed. They must all be at the same depth like this. Now see what happens in here for the comparisons. What happens is that if you look here, you have 3, not just 1 for the binary tree, but now 3 values. In that case, it's strings, could be numbers, dates, whatever. And the idea is that if you look at that, whatever comes first before that word is in here. Whatever comes after this one, but before the other one, is right in the middle in here. Everything that comes after this one, but before this one, comes in here. And everything that comes after this one is in here. Right. So this is the idea. I now have several comparisons. So now when I compare, I start here. Let's imagine I'm looking for merely. Merely, okay, it's before possess. Merely, that's after come, that's after is, oh, here it is. So basically I go here because here there wouldn't be the pointer to the record. I still need to go there to get the pointer to the record. And I found it, right? So it's still logarithmic, but within a node, you just go through the list if you want to over-optimize, you can even go as far as using a binary search in there, but I guess even if you went linear left to right, that would still kind of be okay. And so you go down like this and find it in logarithmic time. That's the idea, right? So we still have kind of some pattern in the way that we put the words in there. All right. Now I still have a few constraints because the number of children, I do have a bit of flexibility. It doesn't have to be the same number everywhere. In fact, I have an interval. So I'm going to say, for example, for that tree, that I want all of my nodes, except the leaves, of course, but all of the other nodes have between 3 and 5 children. 3, 4, or 5. Cannot be 2, cannot be 6, 3, 4, or 5. So look, we have 4 over there. Come is merely, you have 4 children. Thy upon, we have 4 children. That sounds a lot like Shakespeare, and I think it is Shakespeare. That's the way we have these words. So 4 and 4. And the root has 2, yes, but that's because it's the root. So the root has special treatments. That's the only one that is allowed to have less children. Cannot have more than 5, but it's allowed to have less children than 3. One child, no, one child would be ridiculous. If the root has only one child, then you just remove it, right? It's unnecessary to have a root with only one child. So it would be between 2 and the maximum number, right? So this is the idea. For whom is that clear? Right? So we require that we always at all time have between 3 and 5 children, except the root that can have less. The actual values with the pointers to the records are at the leaves. The other values that are up there are only for comparison purposes. This is just to facilitate the lookup, but the real values are at the leaves pointing right back to the records that they come from. Even though you can reuse the values at the leaves for the comparison as well, right? You see that merely is reused as a comparison, possess is reused as a comparison, which kind of avoids having to fake values or make up values. You just reuse those of the leaves. Anyway, so now when you restrict the number of children that you have in a node, that gives you an interval. In that case, for example, so here it was between 3 and 5, here it's between 2 and 4. So we call it a 2-4 B plus 3, right? A 2-4 B plus 3. I should have removed that slide. I didn't remove that slide. The reason why I wanted to remove that slide is that this is not a B plus 3, this is a B tree. And I wanted to remove it because I didn't want to annoy you with the difference, even though somebody asked at the break. But since I have the slide, let me tell you. The difference between a B plus 3 and a B tree is that in a B tree, you can have the values everywhere and pointers to the records everywhere. So in some cases, you will not completely go down. You will stop as soon as you find the word. But again, just forget I said that. So this is why it's a B tree, because everything is colored in blue. But in a B plus tree, only the leaves are colored in blue, right? Okay, so just forget that. But anyway, the reason why we have everything at the leaves like this is that you can very efficiently, imagine you want to list all of the values. Then we just have these pointers in here that chain the whole leaves, and then you go like this, you traverse this. This, in fact, gives you the whole alphabetical list of all the terms, like this. What is the complexity of that? O of n, exactly. In linear time, you retrieve the alphabetical list. Of course, there's no magic, right? Because you know you cannot sort in O of n, but the sorting was done before. The sorting was actually done when you built the tree in the first place. That's where the n log n was. But now you can traverse it in linear time. So that's why we like B plus trees and having only the values on the leaves, because we can chain them like that. And that's very convenient. Now, when we have intervals like this, when we have between 3 and 5 children, we call that a 3-5 B plus tree. A 3-5 B plus tree is a B plus tree in which every node can have between 3 and 5 children, except the root that can have less. Now, you could just make up all the numbers you want, like I want a 25, 137 B plus tree or something, but no, that's not how it works. You do have a few constraints about the kind of intervals that you can have, and it's roughly simple double, right? So the second value is roughly double the first value. There are plenty of conventions. If you try to look that up on the internet, you will find plenty of different conventions, so they will not follow the same. The one that I like to take for my courses is D plus 1 to D plus 1 for some value of D, right? So if I put D equals 2, I get 2 plus 1, and 2 times 2 plus 1, that gives me 3, 5, right? Then you get 4, 7, 2, 3, 1, 1, and so on. What matters is that, again, these bounds of the number of children is roughly simple double, right? So the upper bound is roughly double the lower bounds. Okay, d plus 1, 2d plus 1. Quick question. If I have a 4, 7 tree, it means that the children have between 4 and 7, the nodes have between 4 and 7 children. What is the number of values I can have in a node? Is it also between 4 and 7? How many values can I have in a single node? Anybody? Let me ask it simpler. Imagine I have 4 children. If I have 4 children, then how many values do I have? Yes? 3. It's -1, basically. If I have 7 children, how many values? 6. So if I have between 4 and 7 children, then what's the interval of values? 3 and 6. And that has to do with this. You need to be very careful. There's a -1 plus 1 in there that you need to pay attention to. Because look at that. If you have 2 keys, it's called, people like to call that keys. The values we put in there, they kind of call them keys. Nothing to do with primary keys or anything, right? Even though they could be primary keys if you're indexing a primary key, which is a good idea. But anyway, so if you have 2 values on a node, that means you have 3 children, because one of the children is on the left, one is in the middle, one is on the right. If you have 3 keys, then you have 4 children. If you have 4 keys, you have 5 children, and so on. So be careful, right, about that. And by the way, when I say it's a 3-5 tree, it means that the number of children is between 3 and 5. The constraint also applies to the leaves, but of course the leaves don't have children. So for the leaves, it means that they have between 3 and 6 values, right? But that also applies to the leaves, these constraints on the number of values. For whom is that clear? For whom is that not clear? Let me just repeat again, just to be sure. So you need to be careful that if you count the number of values you have in a node versus the number of children, there is a difference of 1, right? This one is clear, right? If you have a certain number of values, then you have 1 more child than the number of values. So it means that, I hope you will agree, that if I tell you that my parameter, so my constraint for the tree, is that I want between 3 and 5 children, so I'm in this interval, 3, 4, or 5, it immediately translates to the constraints that I have between 2 and 4 keys, right? So what I'm saying is that that constraint on the number of keys not only applies here, it also applies here, even though the leaves don't have children. But that constraint on the number of keys also applies here. Does it make sense? Yeah? Also for you? Okay, yes, go ahead. The arrow, yes, here. It points to the values that are in between. So it's everything that is higher than 1 and smaller than or equal to 2, right? Which obviously wouldn't be an integer, but that's basically what's in between 1 and 2. Lower than 1, yeah, and everything greater than 2, right? But when I say everything greater than 2, you have to be careful, because here, for example, it's everything that is greater than merely, but you also need to consider that you are here. So it must be greater than merely, but also smaller than possessed, right? So it's not everything, it's everything all the way to what you have up there. Okay. Any other questions? All right. All right, so basically children between d plus 1 and 2d plus 1, it means the keys is between d and 2d, right? That's basically how it translates. Okay, so obviously for my slides, I'm using numbers like this. In reality, you're not going to have 3, 5, b plus 3. In reality, you're going to have numbers in the hundreds, right? Like, I don't know, 500 values on every node, right? Because remember that in the end, you want a whole block of the disk, right? Okay, maybe 500 is a lot because the words wouldn't have to be too large for this to work. But anyway, it's not going to be as small as you see here. Okay, but anyway, for my slides, I need to pick small numbers because otherwise, if I put hundreds of nodes, you're going to go crazy. So let me stick to small numbers. So imagine that I'm now building an index. So it means that I'm going record by record. I have a specific column that I want to index, and I'm building my index by inserting into the tree the new values that I find in my database. Just for the sake of the animation, I picked an example with increasing integers, but it's just a coincidence, because in general, it will be just a total random and shuffled order, right? But just for the purpose of the animation. So I have 1, that's my root. It's just that, right? Single node. I add 2, I add 3, right? So now I have a single node with 3 values. How many children would it have, hypothetically? 4, right? But in that case, that's the only node, so it doesn't have any, okay, 4. And now it has more than 5 values, because that would be 6 children, right? And I took, just so you saw, I specifically picked 3, 5 for my example, right? So 3, 5 B plus 3s. So it means that now 3, 5 B plus 3 means between 3 and 5 children, means between 2 and 4 values. So I cannot have more than 4 values. So what happens here? I just inserted a 5th one. That cannot be, I cannot do that. So what do? I split it, right? So I split it into 2 parts, and then I have 2 nodes, and I need to join them, to put them back together. I shouldn't say join, because that's something else. So I put them back together with an extra root node, and I put 4 in there. I could have put 3.5 or whatever I want, right? But it's just convenient to just use whatever smaller value from the right, right? So I just put the 4. Everything strictly smaller than 4 is on the left. Greater or equal to 4 is on the right, so the world is in order. I have 3 values on my left node and 2 values on my right node, so it's all between 2 and 4. So I'm happy about that. So far, so good. Now let me continue to just add these increasing integers, right? 6, 7, that's still okay. 4, 8, oh, that's not okay. Now I have 5 nodes, so I split it. I'm gonna add 7 here. See the split, how it happens? I just add this 7 here and split it in 2. Okay. Then 9, 10, 11, I have to split again, like this. See, I just expand the root a little bit, and now I have 4 children. And now I fast forward, I'm going to not do it one by one, but basically this is what I get if I fast forward a little bit, and I have yet another 5th child, because it's a 3, 5 B plus 3, so I can have 5 children, 4 values in the root. Now at 17, what happens here? That's again too much. So I split it, which is adding 1 more to the root. But again, now we have forwarded the problem, because now the root has too much. We just split it again. We split the root now, and we get a new root. So you see how it grows, right? If you grow, at some point you just add levels and it grows bigger. Yes? It's not the unique way of doing that. You could do it in different strategies. You could split in different ways. You could also have split with 4, 7, 10 on one side and 13, 16 on the other side. In fact, because you have so many possibilities to do it, that's the reason why we don't really give, even to the computer scientists, we don't really ask them to build B plus 3s, because that takes a lot of time. It's so complex to actually implement that we just say, like, this is how it's done. But it's real engineering to actually get it right. Not even necessarily. I mean, it would simplify your code, obviously, if you have a specific rule and you follow it, but there is no specific constraints on the way that you do it, right? It's just whatever you can do to make sure that the number of children and values is respected. That's basically it. And for the rest, everything is permitted, right? Okay. Do we have a question on Zoom too? Yeah.
Why is there no 10 in the second layer?
Where is there no 10? That's because, do you see 10, 11, 12? It's in a leaf. We don't actually need it, because here we are. It's already the leftmost of the right node, right? Let me show it right there. So what is between 10 and 13 is basically this, right? So all of that is on the left of 13. If we added 10 in there, then that would be empty on the left. because everything between 10 and 10, there's nothing, right? So this is why it would be a waste of space to just add a 10 there. Does it make sense? It is basically here, right? So that's for comparison purposes, and this is for the pointer to the records. Are you satisfied with the answer? Yeah. I think that what you mean, so four is present here and here, it's really the idea that here it's the middle one. This is why the 4 is present. It's the middle one, but the leftmost one, then the 1 will not be present here. And the 10 here would only be present one level above, right? Yeah. As I said, it's very complex machinery. So this is why all I'm giving you is an animation, but I'm not telling you the algorithm of how to build that, because again, that's too complex. So I'm not going to scare you with that, right? So all I'm doing is just basically sit back, relax, and watch, right? So this is how a B+3 is growing. It looks like this, right? This is basically what I want to show you. And if you remove nodes like this randomly, then you're just going to have to merge back the nodes in this way, right? So it basically grows and it shrinks as the data gets inserted and deleted. Now, again, remember, in that case, I used increasing integers. In reality, that's not going to happen. In reality, you're just going to get a random order of the coming from the data. All right. And so what you have at the end is a tree like that. And typically, you're going to keep on disk the lower levels. So all the values in there. And the higher levels of the tree, it's a good idea to have them in memory. First, because it's not so much. And then you can do the comparisons faster. And then you're keeping the lower level on disk. Postings list, you can ignore that completely. That actually comes from an information retrieval course that uses these indexes as well. So you can completely ignore that. It's not plus postings list for you. It's plus the pointers to the records of the relational table for this course. All right. So far, so good. All right, so let's do it on data then. Let's do the same thing on data. So imagine that I have this same table. Previously, I built a hash index. Now we're going to build a B+3 index on that. So we're going to go through the table. You see now it's no longer increasing. It's basically random. So we have 20. 20 again, so I don't add that, but I have my pointers. Then 19 is here. So because there are so few values, I didn't take the 3-5 convention in there. I think I picked a 2-4. What did I do? Yeah, I make it break here. So basically, I accept at most 2 values. It's only because my slide is so small and I picked super low value. So let's pretend that I don't want 3 keys and only 2, then I split, right? Just for the purpose of my example. Then I have split like this. Then I have -6 that I need to split again. I can basically rearrange like that. This is fine. As long as I respect the number of children, then this is good. So here I just moved over the 19 to the right. And then 20 is like this. And that's my index. So basically, it takes a while to build. It takes actually n log n, if you want to sound fancy in a party. And now the benefit of that is that I can execute a query like that. Do you see in the where clause? Now we have an inequality. We have a greater than or equal 19, which we could not do with a hash index. We would have had to scan the entire data. But because I have a B+3, I can execute an interval. How do I do that? Well, it's anything greater than 19, right? So I need to look up 19. So I start all over there. Well, I'm lucky, it's actually right there, right? But I basically percolate down here, find it. And then since it's greater than, I take everything on the right. How do I get everything on the right? Rewinding. I have to rewind a lot. Yeah, just so you see, because that hopefully you're going to have an aha moment here. Imagine that I have an interval, everything after should here. Everything after should, look, these pointers here. That gives me the whole thing. So now all I need to do is take all the pointers to the records from here. That gives me the results of my query, right? With these magic extra pointers here that chain the leaves. Yes?
So is for any given table, like this blue list already of this, then we use this access should and just go through some list already.
Yes, so let me well, you have to build it. Here it was pre-built when I showed it to you, but now I just built it, right? So it's 2 steps. There is a first step in which you just inserted the data in your table and you ask PostgreSQL to kindly build the index. Gonna take 2 hours. Then you just wait for it. Then after 2 hours, the index is ready, and then you get that, and now you can use the index, right? That's the idea. And now to explain with the memory and disk. So imagine that we have the memory and disk, like, I'm gonna find my slide again, here. So imagine that all of that, so of course, everything is on disk, right? But that part, I also put it in memory. So you know that the memory is faster on a computer, right? It's much faster to access what is in the memory than what is on the disk. So what happens is, when you start looking for shoe, this is all in memory, so it's going to be incredibly fast to compare, in memory, in memory, in memory, in memory, in memory. Now, you need to read from disk. What will you read? Well, you know you need to read whatever is at the other side of that pointer, right? Because that should is before that. So what you read is the whole thing here. This is what you read from the disk, right? And then if you want to process a query greater than should, you just follow the pointers here and you also load that from disk, you load that from disk, you load that from disk. So you end up basically loading that from disk. But you see that we didn't load that part. Right? That's the idea. We don't need to load everything. We only load the part that we actually interested in, right? Yeah. And by the way, this is when the index is built, right? When you tell PostgreSQL to build the index, this is why it takes a while. It's actually doing all of that, right? Typically, when you build an index, there are 2 possibilities that you experience as a user. Possibility number 1 is, you know what, PostgreSQL, please build my index. I'm out there for 2 hours, gonna be getting some lunch or coffee. Just do your thing and build the index. The database is completely blocked. Nobody can use it. It's building the index. When it's built, it comes back to life, and now you can use it. Possibility number 1. Possibility number 2, PostgreSQL, please build that index, but please, 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 I still need to continue to use the database because my customers are placing orders. So what's going to happen is that PostgreSQL is going to build the index in the background, but a bit slower, right? It's going to hold back a little bit. It builds the index, but you still have some power left to query the data, right? But of course, when you query the data, it's going to be a bit slower to query the data during the construction of the index because some of the CPU is used for the index construction. And once it's done, you go back to normal, but even faster because now you have the index. That's the idea. The first possibility is called synchronous blocking. It means the whole system stops working for building the index. The second possibility is called asynchronous, non-blocking. It doesn't block the database, just the database is slower for a while until it's done, right? Right, and now I can have my query. I follow the 19 and follow all the pointers, and then I get that magically. Now, again, it's not the best example because in that case, it's not a highly filtering queries, right? That's going to return a lot of records. It might take some time. But in general, the most obvious index you're going to build is the primary key. In fact, you don't even need to do it because as soon as you declare a primary key in PostgreSQL, you get the index for free. Well, not for free, it has to build it, but you don't need to ask PostgreSQL to build it. That's what I mean. So you see now why the primary keys are important, right? We saw the candidate keys that give you the possibilities that you can pick as a primary key, but the one you select, the one candidate key that you promote to a primary key gives you an index in PostgreSQL. All right. Now, what if it's not a primary key and you want to manually request an index from PostgreSQL? No problem, you have a command for that. Just like create table, remember, here it's create index. Create view was another one to create a view. So create index, you can actually give it a name like to a baby. I don't really know why you can give a name to an index, right? But you can. Maybe it's when you want to refer to it later or maybe modify it, I don't know. But let's give it a name. Let's call it by title because we want to index by title. On my relational table, publications, and in parentheses, whatever column I want to build the index on. Right? The values in that column are going to go through the hash function if it's a hash index, or are going to be put in the B+3 if it's a B+3. What happens then? So again, you might need to be blocked for 2 hours, go for some lunch and then back or something, right? And then when you're back, you say select star from publication where titled mathematical logic, and that's almost instant. How instant? Logarithmic in that case, because what index do I build if it's logarithmic? It's the B+3, right? That's logarithmic. O of 1 is the hash index. So what happens here is that it builds the B+3 index. If you don't say anything, it assumes you want a B+3, right? Because it assumes you might have intervals as well and so on. So it builds a B+3. So now my query executes in logarithmic time. Very little time, basically, that's what it means, right? And I can change that. That is super, super quick, right? What about that one? Well, this query here is going to be kind of a little bit faster, but not completely, right? Well, actually, this one, if the title is very specific, it might be fast. Look what's happening here. We basically have a where clause that looks at two attributes, year and title. Year is not indexed, right? So we cannot accelerate that part. But title is indexed, and it's an end, right? So the ones with the year greater than 1905 and titled the theory of relativity, that's a subset of those that have the title, the theory of relativity. So what we can do is use the index with the theory of relativity. Then I get a few records, but I'm going to get too many of them, right? I need to only keep those for which the year is greater than 1905. So it means that I use the index, it accelerates it, and then I have a bit of extra work to still do in memory for the rest of my query. This is what usually happens. The index will give you some acceleration, and then there is still a little bit of work to do for PostgreSQL to finish the query, right? Okay. This one wouldn't be faster because the index is on year, right? Publications year, and you're looking for the title. So that would be a full scan of the entire table. Do you agree? Right? Because we are not looking for the right column here. There is a mismatch, right? So of course, you need to pick your indices, right? When you have a website, you know, you anticipate the kind of queries you're going to have, and you need to build the indices that you think will be useful for the kind of queries that you're going to get. Typically, you know the kind of queries because if you have a web shop, you probably also have control over the Java and C++ that builds the SQL queries, right? So this is why you kind of know the sort of queries you will get. All right, and so it's an art and a science to build the indices. This works too, because it's a B+3 by default, so it supports the intervals, right? This will be faster, maybe not fast because that might still be a lot, but faster because you don't need a full scan. This, again, will be slightly helped by the query to only look at the year above 1905, but the part with author Albert Einstein, that you need to do in memory. You need to fully scan all the results of the index. You need to do a full scan of that to get the author Albert Einstein. But you skipped the part before 1905, so you still got a little bit improvements. All right. By the way, you can also have B+3 indices on several fields like this, right? You can also specify the order because remember, there is some sorting in the index. So if you don't want to be ascending, you can also specify descending. You can even say where the nulls are going to go if you want them first or not. And finally, if you don't like the B+3 and you want a hash, then just say so, right? Yes?
If you could say where author and
it's the same. Yeah, it doesn't matter. Mathematically, it's the same. So PostgreSQL is very, very smart. Very, very smart. So it optimizes a lot of things. And commuting like this is the sort of thing that is so simple that it's going to figure it out, right? And every version is getting better. Of course, every year they keep adding more optimizations, but this really doesn't matter. This doesn't matter in what order. Okay? All right, so the hash is how you get it. So the idea is really that it's all about compromises. Basically, if you don't have any index, the updates are going to be faster because you don't have any maintenance to do on any index. So the faster, the writes are faster, but the read is going to be very, 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 very slow. Because every time you read, you need to scan the whole table. So that's extremely slow. However, if you do have an index, the reads are going to be potentially super fast. O of 1 for a hash index, O of log n for a B+3. But the writes are going to be a bit slower because, again, you have all this maintenance to do. So every time you want to update something, PostgreSQL, you're going to say, wait, I also need to update the index, right, with the new data. So the write is slightly slower, plus it needs space, right? An index, you need to make sure you have space on the disk for the index. You cannot build 100 indices, right? There's only so many that you can actually fit on your machine. So you need to pick them wisely, the indices, to really take the time to think about those you want. Here, I could have removed that, so I'm not even going to skip through the details, but you can look at it offline. It's just as a small exercise. It might be there still the exercises for you, actually. It's just about asking, is it worth to have an index or not worth having an index based on my queries? Oh, we have a question. If we originally input the data.
If we originally input the data or created the index according to the year of the book, but now I want to search according to the name, does it need to take a full scan now?
If you index on the year and only query on the author, not on the year, then it's a full scan of the entire collection. In other words, the index then is totally useless, right? If it's not the same attributes, right? Okay. So now you can look at it offline. It's just an exercise like, imagine that I have queries with updates and non-updates, right? I have like 2 possible queries and then an insertion and so on. And I'm basically asking myself, should I build the indices? Should I build index 1? Should I build index 2? Or is it totally useless? That kind of depends, right? Imagine that you are in a workload where you insert a lot of data, but you very rarely query it. Then it's probably not worth the indices. It would only slow down the inserts. But imagine, on the other hand, that you have plenty of query 1, 2, all the time, insertions, very rare. Then it's worth having an index. But where is the threshold? At what percentage does it start to be worth having an index? And you kind of compute things with simple models like this in terms of costs, right? No index, the costs of an index or insertion is low, but the queries are very slow. With one index, then one of the queries is faster, but updates are a bit slower. With only the other index, is the other way around. Query 2 now is faster, but not query 1, and insertion is slower. With 2 indices, both queries are faster, but insertion is even slower, right? And then you can compute an average, but again, you can feed in the percentages, right? Imagine that you have A% of Q1 and B% of Q2. Then you have 1 minus A minus B, right? I'm just assuming I'm expressing my percentages as doubles between 0 and 1, right? So it's 1 minus N, 1 minus B, and then you just do the math, right? You can compare the values like this, and then you can conclude that, for example, if A plus B, so the proportion of queries is more in that case than 33%, so 1/3 of the time you have your queries, then it's worth having the indices, right? Just look at it offline. I'm not going through the numbers, but just to show you that you can do that sort of math to figure out, do you need an index? Do you not need an index? And then it just gives you an intuition, right? But whoever has a website needs indices. Imagine that Amazon didn't have an index. The catastrophe that it would be. Every time you have to come back in 2 days in order to get the results of what you're looking for. So the indices are so important in a relational database system. And again, if you use Python, you don't have that. If you can go ahead and use a notebook with Python and pandas and so on, you're not going to get that fast. With a relational database, you get full speed, instant lookups. That's the benefit of a relational database. And you get it for free without having to do anything, because all you need to do is create index, blah, blah, blah. Just takes a few seconds of your time. All right. That's it for today. So thank you very much. Next week, we will look into data cubes, because the whole semester we've been looking at tables, but guess what? There's other shapes out there. So next week, we are going to look at data cubes, and then the data architecture, as database architecture, and then we'll wrap up with the celebration of the end of the semester with the TAs and everybody. Thank you very much, everybody. Enjoy your meal, enjoy the exercise session, and I'll see you next week. Thank you very much.